Hi! In this video we continue working with the Frenet frame of space curves, and we introduce the notion of torsion of space curves. The main goal now is to study and to compute how quickly the tilt of the osculating plane changes from one point of the curve to another point of the curve next to it. More precisely, we introduce a function, the torsion, as a measure of how quickly that tilt of the osculating plane changes, as for example, as the image we have on the screen. We consider a space curve, and for simplicity, we consider the arc length parametrization of it. As we already saw in a previous video, at each point of the curve, we have an orthonormal basis called the Frenet frame, formed by the tangent, the normal, and the binormal vectors. The osculating plane is spanned by the tangent vector and the normal vector, so their cross product, the binormal vector, is a normal vector to the osculating plane, and it encodes the tilt of it. Now compute the variation of the binormal vector. As it is a unit vector, by taking the derivative of the identity in the screen, we obtain that the vector b' is orthonormal to the binormal vector. Taking now the derivative of the cross product of the tangent and normal vectors, we obtain the expression in the screen for the derivative of the binormal vector. And by using the first Frenet equation, we obtain that the vector b' is orthogonal to the tangent vector. As b' is orthogonal to the binormal vector and also to the tangent vector, we conclude that b' is parallel to the normal vector. That is, b' and n are proportional. We denote by tau the proportion between these two vectors. Multiplying by the normal vector to both sides of this equation, we obtain an expression for this new function tau. The function tau is called the torsion function, and it measures the variation of the binormal vector. We now look for a useful formula for the torsion. After some easy but rather long computations, we can express the torsion as the following quotient. The quotient between the mixed product of the first, second, and third derivatives, and the square of the curvature function. Geometrically, the mixed product is the volume with sign of the parallelepiped defined by the three vectors. Hence, the volume of the parallelepiped is 0 if and only if these three vectors, the first, the second, and third derivatives, lie on a plane. We now do an example. We consider a curve parametrized as now you have on the screen. We used that example in a previous video. We compute the first derivative, and it's easy to check that the curve is arc length parametrized. We compute the second and the third derivative, and we see that the first and third derivative are proportional. This fact implies that the torsion vanishes identically. Moreover, note that the x and z components of the parametrization satisfy the equation at the bottom of the screen. This equation is the equation of a plane, and then the trace of the curve is constrained to that plane, x plus z equals 1 over the square root of 2. In other words, the curve is constrained in a plane, and the torsion function identically vanishes. In fact, we are going to prove this general result. The trace of a curve is constrained to a plane if and only if the torsion function vanishes identically, or equivalently, the binormal vector is constant. We prove now this proposition. First, we assume that the curve is constrained to a plane with equation, the one you have now on the screen. As the curve is constrained to that plane, it satisfies the equation of the plane, and by taking the derivative of the above equation, it follows that the vector w is orthogonal to the tangent vector of the curve. Taking again the derivative after some computations, and taking into account that the unit tangent vector is orthogonal to w, it follows that w is also orthogonal to the normal vector. Hence, the binormal vector is parallel to w. Therefore, it is constant and the torsion vanishes identically. Conversely, we now assume that the torsion vanishes identically. This implies that B' is 0, and therefore the binormal vector is a constant. We call W this constant. We compute the derivative of the inner product of the parametrization with this W. This derivative is 0, and then this inner product is constant. Hence, the trace of the curve is constrained to the plane, the product of W, x, y, and z, that constant. We finish this video with the formula of the torsion for curves that are not necessarily arc-length parametrized. This is the quotient of the mixed product of the first, third, and second derivatives, and as the denominator, the square of the norm of the cross product of the first and second derivatives. The mixed product can be computed as the determinant of the matrix defined by the first, third, and second derivatives. As these vectors are 3-component vectors, the matrix is 3 times 3. And taking advantage of the properties of the determinants, we can change the order of the last 2 columns, and we have the formula at the bottom of the screen.